on phenomena of random matrices by Stanislaw Szarek on this subject.
Thank the chair for the introduction and to the organizers for inviting me. Okay. Well, the talk is roughly on the same topic, or at least the same starting point as Guillaume's talk yesterday. So it's about generic properties of random quantum marginals or random quantum induced states. So this is the abstract that well, it's basically the same statement as yesterday. So what we have is we have the following situation. We have a system consisting of, well, I should have erased this in preparation. So we have a system consisting of n particles, and then we have two subsystems, A and B, of k particles each. So now the remainder we sort of identify with the environment, and that of course is n minus 2k. Now we're assuming that the entire system is in a random pure state, by which we mean that it's a state uniformly distributed or on the sphere of the corresponding Hilbert space, well, or the projective space, which is the same in this case. And now we are considering the marginal distribution just of this distribution of the system AB, and we ask all kinds of questions, like, for example, is that marginal or that induced state typically entangled? Is it typically PPT or APPT? Okay, name it. Okay. Now, so what I'm going to do is I will present a general scheme for handling such problems, such questions, with exemplified in the case of entanglement. So in the case of entanglement, there is this sharp transition, that transition threshold, which is asymptotically k equals to n over 5 if and so if the number of particles in each of the subsets is less than that threshold, then they do not share entanglement, and if it's larger, then they do share. Now, it may happen that if this threshold actually happens to be an integer, is that there will be an integer for which we do not know. But if that integer just is sitting on that threshold. Okay. Well, the summary. So the first part basically will be just recalling the notation and setup that was already in Guillaume's talk. Then I will state the main result, and then I will try to give some elements of the proof. So the setup. So well, we have, just for the notation, we have set of states is denoted by D. Set of separable states for some assumed fixed by partition is denoted by S. And whenever we talk about S of Cn, then we implicitly assume that this Cn is represented as a tensor product of two copies of CD, and in particular that n equals to D square. So those letters, whenever you see N or D, they mean exactly this throughout the talk. And this was the same as in Guillaume's talk. However, Benoit spoiled the effect because he had different notation. So this may be a little confusing at this point. So now important features of those states are that those are convex bodies in the hyperplane consisting of trace one self-adjoint n by n matrices with the maximally mixed state as the interior point. Moreover, the maximally mixed state is the only point that is invariant under isometries of either set.
Sorry, can you remind me the definition of a mixed state?
Mixed state, same as in previous one. Trace, positive semi-definite, trace one. Okay, so that's just this. Now this approach, as I said, will work for many other properties as long as they have some minimal permanence properties with respect to this decomposition or whatever, decomposition or not. There could be multipartite and so forth. Of course, it works in principle, which means that we may not be able to calculate some geometric quantities which are involved in studying specific phenomenon, but in principle they reduce the question to calculating some geometric parameter of some convex set. Okay? So the setup is as follows. We are looking at this. So this is the state, the situation corresponding to this picture, right? We have tensor product of three systems. This is environment A and B. Now here we have, so here I will sort of describe why there is this 1 over n over 5, right? So Guillaume already did this calculation. I did it in a slightly different language. So each of the particles is represented by c to the d. So we assume that there is d level particles. So here we have cd to the k, cd to the k, and cd to n minus 2k. And so now we can write this in this form where d is d to the k and s is n d to the power n minus 2k. So if n equals to 5k, then n minus 2k equals to 3k. And in that case, s equals to d to the power 3. So basically, the reason for 5 is that 1 plus 1 plus 3 equals to 5. Right? And anything that whenever we have any other property for which there is something happens at the level d cube or d to the power something, then we are going to have a corresponding threshold with the same algebraic derivation, so to speak. Okay, so well, this is the pure state. So if the entire system is in this pure state, then the marginal is the partial trace. You have to trace out the environment. So this is, in this case, this will be c to the s if we identify this with c to the s. Right? And another point of view is that if we identify this pure state, which is a unit vector in this space, with a matrix, n by s matrix, right? So this is a little bit tricky because it's not a linear identification, but only sesquilinear or whatever. Then, in that identification, the partial trace becomes just the square of the absolute value of your matrix. Right? This is just a little linear algebra, and that was already, well, probably almost everybody knows that, and this was shown up. So, okay, so the bottom line here is the following: that well, maybe I do those lines. So if you have a random point on the sphere in the product space, and at this point we don't even care about whether this is a tensor product of something or not, then the marginal is a random state on Cn, of course, right? Random here, random there. If this is distributed uniformly on the sphere in that Hilbert space, then the corresponding matrix, which is n by s matrix, is distributed uniformly on the Hilbert-Schmidt-Frobenius sphere in n by s matrices. Now those are complex n by s matrices of course, so nothing self-adjoint, no nothing, right? So this is just, for the moment, this is just reformulations. Okay, so what we have is we obtain this way, whether we look at it this way or that way, we always obtain induced states on Cn with an additional parameter S, whether we look at it this way or that way, and we'll prefer looking at it as a dagger, a dagger. Okay. So another way to represent such situation is to consider a standard complex n by s Gaussian matrix, and then B, then you consider BB star and then divide by the trace, so you obtain a state. And so this way we obtain, as explained in by Benoit most recently, we obtained a normalized complex Wishart matrix. And actually this, we are not going to use this well very strongly, but that's yeah, that's basically a constant, right? So from some point of view. So okay, so now we are sort of in a situation we reduced our problem, so to speak, to a familiar random matrix situation. So we have the idea basically is that so much is known about Wishart matrices that we should be able to figure it out, whether such matrix is typically separable or typically not separable, right? Okay, so so here is the statement. So there is a threshold which occurs on the level which is approximately d cube. So it means this parameter s is when this parameter s passes that threshold, which we don't know exactly where it is, but we know that it's between d cube up to logarithmic factor, it's d cube, and some universal constants, right? And then what happens is that if this ancilla, dimension of the ancilla is smaller than 99%, well, arbitrary epsilon here, of that threshold value, then the marginal is separable. Excuse me, if, okay, then marginal is actually separable with very small probability, which means with probability almost 1 is entangled, and the opposite behavior if it's larger than that, then it's typically separable. Okay, and then those are like specific estimates. Those probably aren't optimal. We sort of suspect that what we should have here is we should have here d to the power 4 or n square, I think, and this is about a cube, but this is already not bad. Okay, so then so corollary is a statement in the abstract. So now I already explained how the calculation, why the what's the relation between the 1/5 and this exponent here, right? And Guillaume explained that also yesterday. So the only thing that I sort of need to explain is why there is a sharp threshold, right? Because, well, the thing which is a little bit bothering is that here we don't exactly know how much that is. There is still quite a gap here. However, we know that whatever that threshold value is, just from 99% to 101% of it, there is a jump from one type of behavior to the other type of behavior. Okay, here actually there are some various references which contained similar results in the same direction. So the next slide will be explaining why we do have the threshold phenomenon, why the sharp threshold. So now the thing is this, that if you replace k with k minus 1, so this kind, let's go from larger k to smaller k by 1. Now what happens is that well, we decrease this by 1, then decrease this by 1. So this means that the dimension of corresponding to the first subsystem of the Hilbert space corresponding to the first subsystem decreases by factor d. So it's, if d is even a qubit, right? If d is 2, then it's at most d over 2. So this means that, and on the other hand, s increases at least by factor d square, which means at least by 4, right? So, well, so since it takes only an increase of s by a factor 1 plus epsilon over 1 minus epsilon, so if we increase it by a factor at least, is this correct? Yeah, okay, at least 4, then we for sure jump in one step over the threshold. Now it may just happen that if our k is exactly on the threshold, then nothing happens. But that's why I had strict inequalities in the statement. Okay, so here there are some fine points here, because actually we are changing at the same time s and d. So one may worry that things get spoiled by that, but if you denote by pi ds the separability of that state under those parameters d and s, then this is a decreasing function of s, and so changing d actually only works in our favor. So it's enough to look at s, and so that theorem is good enough, right? And here there is a question: is we do not know whether the behavior of this probability is monotonic with respect to s. It should be, but we don't have a proof. We know that roughly it increases, but whether by changing s just by 1, whether it always increases, we don't know. Okay, so yeah, okay. So now, now let's so basically, well, let's go now to sort of overview of the proof of that theorem, right? So the situation is that, well, this is just the notation. So I want to rephrase the entanglement property. So what we have here is a set S, which contains the maximally mixed state. Those are separable, contains maximally mixed state. It's contained in D, and it's contained in the hyperplane of trace 1 matrices, and it's contained, which is a hyperplane in all the n by n self-adjoint matrices, right? So now what we do is we translate everything to the origin. So what I want to do is I want to think of H1 as a vector space with identity over n as the origin. So a priori just an affine space, so I can make it a vector space by choosing the origin. And alternatively, I may just translate everything to the origin. And then I have a set S0, which is just S minus identity over n, which is contained in translated D0, which is contained in the linear hyperplane. And the advantage of this is that I'm working with vector spaces, so I will not. So everything will make sense as we are normally used to for vector spaces. Okay, but it's just a rephrasing, right? So now there is another tautology, which is that a state is unentangled or separable if it belongs to S, right? So if it is the same thing tautologically as when you subtract the identity over n, then it belongs to the translated S. That's tautology, and this is equivalent. It's again tautology to the gauge of the set S0 evaluated at that difference being less than or equal than 1. Now, what is the gauge? The gauge is, well, the gauge is of a if you have a set K which contains 0 in the interior, then the gauge of that set is it's a function which should be thought of as the norm, with K as the unit ball, and it is when K is symmetric. So that's the size of the smallest blow-up of K, which contains X, right? So if K is the unit ball, then This is the smallest radius that contains, so that the ball of radius R contains X, right? So, but this can be also defined for non-symmetric sets, and in this case we have, except for the trivial cases, well, for the very low dimensional cases, those sets are non-symmetric. Okay, so okay, but this is really tautological, right? I'm saying that basically what I'm saying is that a vector belongs to a unit ball if and only if its norm is less than or equal than 1. I didn't say anything smarter than that up to now, right? Okay. So of course, by contrapositive or whatever, it's untangled. Only a vector has a norm greater than 1 if and only if it's not in the ball, unit ball, close to unit ball, right? So that's okay. So now what we need to show, right? This is where the work starts. Is we need to show that these things here, this inequality here and this inequality there, happen with probability either 1 or 0, depending on the relation between S and D, right? So there is this exponentially small probability of those error set, exceptional set. Outside of that very small exceptional set, either this or that has to be satisfied so that our conclusion holds. So there is a standard procedure for approaching some things. It's use concentration of measure. And so then we have which reduces the problem to evaluating just the average of the quantity of interest, which in this case is this quantity, right? So this is a random matrix, random state, if you will, and then you apply some functional to it. So this is a real variable. Oops, what happened? I went 20 pages forward.
Retain the proof is very quick.
Okay, so here we are. Right? So now so basically the problem is reduced to calculating the expectation of that quantity of interest. We want to show that with large probability this quantity is less, this quantity here without expectation, the random variable, is smaller than 1 or greater strictly than 1. Okay? So instead we show two things. We show one thing is that the expected value of this random variable is just a little bit better than, either a little bit smaller than 1 or a little bit larger than 1. And the other thing is that we show that because of the phenomenon of concentration of measure, that function is practically constant. And so it takes on a set of very large measure the same value, or essentially the same value, right? So since we gave ourselves this margin of error, so we'll get that with large probability in this first case, with large probability this random variable is less than or equal than 1, and in that case is strictly greater than 1, and we're done. And this is a standard procedure. So there are two steps. First, you have to show you have, well, which are of different difficulties, and the second, as you may notice in this here, the second step is always the easier one. So to show that concentration, once you understand, once you know understand concentration of measure, to show the second step is reasonably routine. It's not completely trivial. It uses some relatively deep results, but at this stage it's relatively routine. Now this first step is sort of more specific to those to this particular situation, and so it requires a little bit harder work. Okay, but basically we split our problem into two sub-problems. One problem is to show some kind of smoothness of this quantity as a function of A, right? Now again, A, remember, it's a point on a Hilbert-Schmidt sphere, right? In n by n matrices, in n by s matrices. And and the second one is the expected value of that quantity. Okay. So let's start from step 2, which is sort of easier. So I'll be able to quickly go over it, hopefully. So this is smoothness and concentration. So first, smoothness, right? So we have to, smoothness means you have to estimate the Lipschitz constant. It's not absolutely necessary. There are some other continuity. It's also possible to work with. But so this is a composition of two operations. The first operation is we associate it with A, the thing whatever is inside here, and then we take the gauge, right? So we show separately. We separately estimate the Lipschitz constant of each of those operations with respect to the appropriate matrix. So for the first step, we do it from Hilbert-Schmidt norm to Hilbert-Schmidt norm, right? Those are matrix here, matrix there, right? So that sort of makes sense. Now, and the second operation is just the taking the gauge. So in the domain, we take the Hilbert-Schmidt norm, which has to be the same as here, so that things make sense. And in the range, that of course just real numbers, so there is no choice, right? So again, let me start from the second one, right? So this is a very standard procedure, because what we are doing here is we are really comparing two norms. This is not really a norm. It's a gauge, asymmetric, but it's the same rule as for comparing two norms. You just have to find the in radius or out radius in this sense or that sense. It's a very geometric question, and in this case, since we are working with the Hilbert-Schmidt norm in the domain, which is Euclidean norm, so what we have to find is the in radius of this set S0, which has to be necessarily centered to the optimal ball. Euclidean ball has to be centered at 0, which remember was shifted from the maximally mixed state. And that is very well known. That was calculated by Gerwitz-Barnum in 2002, and it's the same thing as the, now even though S0 is a smaller set than D0, the Euclidean in radius is the same in both cases, and there is an explicit formula, and this is less, it's at greater or equal than 1 over n. So now for the Lipschitz constant, we get that it's less than or equal than n. Well, actually equivalent to n is very, very close to n, right? So here there is no, you cannot correct this. This is how it is. Now, what about the first what about the first step? We're associating with A the absolute value square, and then shifting, of course, doesn't change anything. Now, of course, this is not Lipschitz, right? This is not a Lipschitz map, right? This is like x squared, right? However, if you restrict it to a bounded set, the sphere, it becomes Lipschitz. And so this is like basically saying, what I'm writing there is basically saying that the function x squared restricted to the interval -1, 1 is Lipschitz with constant 2. It's pretty much the same argument works, right? So actually, even if we restrict to the ball in the operator norm, that even works, and that allows for some improvements. Okay, so the composition is going to be 2n Lipschitz. So let's just do the calculation. Well, not the calculation. We first let me recall the Levy's lemma, which tells us that functions on Euclidean spheres that are Lipschitz are very well concentrated around their means or medians. And it doesn't matter whether it's mean or median, because if they are concentrated, then mean and median are very close to each other. And so there is what, oops. Okay. So what do we have? We have, so there is this, well, you just have to believe this. This is Levy's lemma, concentration of measure. So deviation from the median or from the mean by more than epsilon may happen only on the set of normalized measure or normalized invariant measure on the sphere, which is exponentially small in the dimension, and then epsilon square, and then the Lipschitz constant must enter this way, because epsilon over L, it rescales by epsilon over, it must depend only on epsilon over L by sort of obvious reasons. Okay, so now when we verify, so we just apply it straight as it is. So now we just have to realize what is what. So now here we are on the sphere of complex n by s dimensional matrices, right? So the real dimension of that space is 2ns, right? So m here equals to 2ns. Now Lipschitz constant is 2n at most, right? Actually it's less than that maybe, but doesn't matter. So when we calculate this, the thing that enters here in front of epsilon square, then it's m over 2l square, which is 2ns over, do I have it right? 2, well, I think should be 8. I think it should be 8 here, right? Because it's 2n, you have to square it, and there is 2, right? So I think I missed the factor 2. But in any case, I think it's after dust settles down, it will be s over 4n. Okay, so that's not that's a very wasteful argument, right? That's a very wasteful argument. However, for our purpose, it is sufficient, because you remember, well, I actually advertise that this is what you will get in the exponent here is something which is like there will be an s epsilon square or something like that, or there will be s in the exponent. Now I don't get it. I just get s over n, which is much worse because it was negative constant. So, however, remember that we are ultimately interested only in the range where s is d cube, which is about n to the power 3 over 2. So this ratio is like n to the power 1/2. So this still is allowed to have epsilon which goes to 0 as n increases or d increases, right? So here, and still to get very small probability, right? So now this is, as I said, this is very wasteful, and now I'm going to flash 2 next pages which contain a better argument, and at the end you get omega s, but but that's a little bit harder to follow. And so this is the type of, for those of you who know, this is the type of an improvement that Hastings had in his Lipschitz constant. This is basically the same idea. But okay, but in any case, for getting generic behavior without very good estimate on the probability, what I wrote 2 slides back is good enough. That will not work though for the property which is like PPT, for which the threshold value is proportional to n. So for the PPT property, you really have to do this better argument or a version of it. Okay. Okay. So now what do we know? We are what did we do? We did the second step. So now 1 step backward, we do the first step, right? So again, the second step was that assuming that we can estimate properly estimate the expected value, then we can conclude from that we can use the concentration phenomenon to deduce the advertised behavior of those random marginals. So now we have the estimating the expected value. Now what is the difficulty here? The difficulty is as follows, that there is no formula for this quantity here, well, without the expectation, because if we're able to calculate this formula efficiently, if there was a nice way to express it somehow, then of course we would be able to decide when states are separable and when they aren't, and we know that we cannot. Right? So this is somehow unavoidable, that there is no neat way to calculate this, at least very precisely, right? Maybe what is known is that it's very precisely. So there were some, I'm cheating a little bit because this is really to calculate. It's known that to calculate very precisely is very hard. But maybe calculating it on the level of precision that is needed for us, maybe that wouldn't be that hard. But well, anyway, that's maybe it's easier, but we don't know. But in any case, there is no formula. Right? There is no nice formula for calculating this. So yesterday's argument given by Guillaume was based on working with the dual picture, which is with the dual quantity, which is the gauge of the polar. Right? So now what is the polar of a set? Polar of a set is, well, if you haven't seen it, then you should think of it this way, that if you have the unit ball with respect to some norm, then the polar is the unit ball of the dual space, the dual with respect to the dual norm. Right? Okay? And this is what it is, except that it allows non-symmetric sets. So the yesterday argument used estimates on this dual quantity, which was the mean width of this set as 0. Now there is something which maybe people who are not used to it find confusing, that whenever you calculate the mean of width 0, then the dual quantity appears here in the gauge, but that's sort of how it is, right? Because when you calculate the width of a set, then this means that you hit it with functionals, right? And so that happens unavoidably. Okay. So now what do we do? So the argument is again based on two sub-steps, and both of them are not entirely trivial. So the first step is a random matrix argument, and it tells us that in order to calculate this estimate, now remember, this is a random matrix. It's a sort of like a shifted normalized Wishart matrix, right? So this is something like a very well understood object. So calculating that is equivalent to calculating something which is geometrically simpler, has more immediate geometric meaning, and namely is the so-called the mean width of the polar of this set of the set as 0, right? And the polar is defined by that obscure quantity, whatever, by that formula, the dual formula, right? The dual norm in the dual norm. Okay. So now this is just definition, right? This is just a definition of the mean width. That's for any set. That's how it is defined. This is just a factor which happens to be present. If there was no factor, this would be just definition for any set. That's how it is defined. Okay. So basically, the idea again is that you are taking a direction. We look how wide that set is in that direction. Well, actually divide by 2 because this is, and then we average this over all directions. That's the geometric meaning. Okay. So here, we are connecting, we are relating some this random matrix quantity with some more geometric quantity, right? And this works in the regime where both n and s over n goes to infinity. If in the other cases when n is less than s, or when it doesn't go to infinity, maybe even, then there are two-sided estimate. Okay, when s is greater than n, but the ratio doesn't go to infinity, then there are two-sided bounds with universal constants, which also allow for some drawing some conclusions. Okay, so this is the first sub-step, and the second sub-step is pure geometry, which is estimating this quantity here, right? And this is just what is the mean width of that set that is defined as the polar, oh sorry, as the polar of that translated set of separable states. Okay? So there is a random matrix state, random matrix fact, and geometric fact. And once these are shown, this is actually, it's very easy to see that everything is settled, because what? Well, let me. Okay, so go to here. So in that case, the threshold value will be, we choose as a threshold value the square of that width, right? And why is it so? Why does it work? Because then, for example, if S exceeds the threshold value by the fraction ratio 1 plus epsilon, oh, sorry, okay, then what happens? Then, first of all, this quantity equals to that quantity. I am just copying that. This is the substep 1. Now, this equality is just definition of the threshold value, which I gave there, right? And then this inequality is just because S is larger than the threshold value sufficiently, and this is just the asymptotic expansion, or whatever, linear expansion of 1 over square root of 1 plus epsilon. Okay? And so what we get in this case is that the expected value that you are after, the expectation, is less than or equal than 1 minus epsilon over 2. Well, maybe not quite 1 minus epsilon over 2, maybe 1 over epsilon over 4, because there is this approximation here, so we have to maybe work a little bit, well, be a little bit more careful. But in any case, what happens is that this is separated from 1. It's below 1 by certain quantities that we can put our hands on, and so the entire random variable must be with large probability below 1, which means that with large probability it's the corresponding state is separable, right? Now, and the argument in the opposite direction is the same. It's just well, it's great if it's smaller than, then you still get separation from 1. Okay, so okay, so we have those two steps, which are so let me just very briefly indicate what enters into those substeps. Again, I'm starting from the second. Okay, so maybe I will get the entire page to speed up, and so that I don't press any buttons now, right? Wrong. Okay, so we want to prove this. This is just a statement about this particular set. There is nothing about random matrices, well, almost, right? So now this is the, so again, what is known is the quantity, the dual quantity. So this has been calculated some years ago, and it's known what it exactly is asymptotically up to the order, right? So for comparison, for the set of all states, this is 1 over d, right? Remember that we're in this space which is d times d, which is d square dimensional, right? So this is for all states it's 1 over square root of n, which is 1 over d in our notation, and this is smaller by that factor, in the exponent. Okay, so now one always has that the width of the set and of its polar multiplied is greater or equal than 1, and this is basically Hölder inequality, right? And then there is there are deep results in functional analysis, or in Banach space theory maybe, that in some cases this inequality can be almost reversed, and that happens when this set K is in the so-called L position, where whatever it's called L position for historical reasons, doesn't matter what L is. And what being in L position means that it's in certain sense isotropic. So you can always achieve L position of any set by appropriately rescaling certain directions. Right? And once that happens, then you have almost the inverse inequality, namely the product of the two is at most of the order of logarithm of the dimension of your set. Okay. Okay. So once if we had that, right? If we knew that for our k, or for our 0, k equals a 0, we do have such an estimate, right? That this is bounded from above. Then we know. Well, then we could calculate just that this would be at most 1 over the width of S. So this gives us d to 3 over 2 times logarithm of the dimension, which is the power of d, so it's logarithm d in either case. And so when we square it, which is by definition how we define the threshold, then we get d cubed to the power times square of logarithm, which is exactly as advertised. And the lower bound is even easier because you just use this, right? So that's how you get it. But because here you know that this is exactly the correct order. Okay. So if we knew that, right? So if we are able to apply it, then it will be done. Now, well, actually, okay. So when does one know that the set is in an L position? Well, this is, well, I said that it's a certain way of being isotropic of balance. So in particular, if the isometric group of k's are irreducibly on the entire space, then this set is in that L position. In our case, this is not true that we have this irreducible action, but it's sort of almost true, because if we do the isometric group, which is local unitaries, then the space splits into 3 factors, 3 irreducible factors, and one of them is huge of this dimension, well, square of d square, and the others are of, so that corresponds to trace 0 tensor trace 0 and trace 0 tensor identity trace 0 tensor identity tensor trace 0 vaguely. Right, so and then it follows from the general theory that rebalancing that we have to do to bring our set into the L position is just a dilation if each on the invariant subspace, and since those dimensions are negligible, then we can use some rough estimates, and we can conclude that even though not necessarily we are in the L position, the estimates still hold. Okay, and so this works. Well, oops, there was actually the MM star estimate required symmetry, and here we don't have symmetry. But there are some workarounds which are relatively straightforward. Yeah, I should finish, right? I guess, right? Well, you advertised 45 minutes, right? Okay, so we're sort of basically done with we are down to the last sub-step. So let me just mention a few things which enter into the picture. So now this is a random matrix statement. We have to show that this expected value is the same as that average. So there are and this is, it turns out that this is true for any gauge, or at least for any reasonable gauge. Maybe. Let me qualify my enthusiasm here. So here we are basically forgetting what separable space are. What only matters is this random matrix ensemble, right? And how the averages of gauges compare with averages on the sphere, right? So the trick is a linearization. So what we show is that this AA square, AA perp minus multiple of identity thing can be, for all practical purposes, approximated by a multiple of the Gaussian unitary ensemble conditioned to have trace 0. Right? Now here so now Gaussian unitary ensemble is usually defined by either one talks about entries being Gaussian independent except for self-adjointness, or one gives the density formula. But what here the best way to look at it is that Gaussian unitary ensemble, this is given by the standard Gaussian measure on the space of self-adjoint matrices. In this case, on the self-adjoint trace zero matrices, right? So this is basically, forget what that is. Just we have the standard Gaussian measure, right? Okay. So basically, what we have to we approximate this ensemble by a better well-known ensemble, which is Gaussian unitary, and then we use the formula which relates spherical averages to average with respect to the Gaussian measure, because the Gaussian measure has spherical invariance, rotational invariance, there is certain parameter which only depends on the dimension if it's approximately square root of the dimension, which relates the expectation here, or average on the sphere, and the Gaussian expectation if we plug in here the Gaussian random variable, okay, the Gaussian random matrix. Okay, so if we believe that, it's a question of only putting things together. And so what do we have? We have this is the statement we just said that this multiple of Gaussian unitary ensemble approximates our ensemble. Okay, then this equality here is just saying that the Gaussian average is a fixed multiple of the spherical average, and this is the square root of m, which appears there, and it cancels out with that n, so we are left with 1 over square root of s. No, and which is exactly what is needed. Okay, so what is that parenthesis doing? Okay, so there is so the sanity check is that one checks what Benoit was calculating. One checks the supports of each of those ensembles, and this can be at least on the heuristic level figured out, because we know that by the Marchenko-Pastur for large in the asymptotic limit, the Wishart distribution follows the Marchenko-Pastur law, and then the Gaussian unitary ensemble follows the Wigner law. And if we look at the intervals on which they are supported, we get that asymptotically those are the same intervals. So at least it's not that bad, right? So both of those ensembles, the one here and the one there, are supported on the interval minus 2 over square root of n of s. Well, this is here. This is the Marchenko-Pastur support. This is Wigner, which is appropriately divided here. So this is what we get. Now, this is actually not. So again, as Benoit was saying, usually the the limit theorem for random matrices are stated. Maybe let me show the entire page again. Are stated for empirical spectrum, sort of for the spectral measure, empirical spectral measures, or empirical spectral, well, whatever distribution, and so what is? But actually, we also, in all those cases of interest here, we also have the convergence of the extreme eigenvalues, and this can be subsumed by. We found convenient, and so I wanted to advertise it to subsume this by convergence in the infinity Wasserstein distance, which is defined for two distributions on the real line. I guess, right? Yes, on the real line, as infimum over all representation of the couple xy on a common probability space of the infinity norm. Right? So if you have two random variables so that you can just move them very add something which is small in an infinity norm to get another representation of the other, then we say that those are near. Okay, so and now this follows from the general theory. Once we believe that there is convergence in this Wasserstein distance, and now the last thing that I wanted to point out is that it still is not totally obvious, right? Because even if we know that this and that converge to the semicircular law, the Wigner's law, with the semicircular density, so they converge to the same object, so they somehow must be close to each other, right? If this converges, this and that converge to the same object, then it still doesn't exactly follow that after you apply the gauge, the expectations will follow, and this is because those gauges are not uniformly continuous. The Lipschitz constant explodes with the dimension. So there is some more finesse that is needed, and that finesse is provided by majorization, right? So here, well, let's just leave it out. So there is a, okay. Well, so by majorization, which maybe I will say something about just this slide. So this was defined, I think, the first day of this workshop. So there is majorization for two sequences in Rn. This is equivalent to several properties. One of them is that for every permutational invariant convex functions, we have a domination. And another equivalent property is this one. Okay. Now, this property is related to weak convergence of measures, because this can be expressed, this, if you divide it, if you normalize this sum, then this can be rewritten as integral of phi, where phi is u minus t, with respect to the empirical measure supported as at coordinates of x. Okay, and on the other hand, this assertion is exactly in the spirit of well, the proposition which is on the previous page, which is about dominating certain gauge, having inequality for gauges. Okay, so okay, I will stop here. Thank you very much.
All right. Well, we have time for questions.
Serious?
Yes.
In terms of these phase transitions, are there other quantities you would expect to have such a similar behavior, besides just looking at separability and entanglement?
Well, basically what are the ingredients here? The only ingredient for having phase transition is that you have to be able to associate with your property a certain quantity, and that quantity has to be reasonably smooth, reasonably continuous. Doesn't have to be extremely continuous, but when any reasonable continuity will do it. So, for example, every property that is intermediate between separability and just being a state, or even worse than being a state, that is good enough. So PPT or anything of that nature goes there. Then, so then you will be, under those assumptions, you will be generally able to show that there is a threshold. To be able to calculate the threshold, that involves a specific calculation for that particular quantity, which may be doable or not. So now, we can calculate this in well. For example, Guillaume mentioned already, when we have two splitting into sets of this not the same size, that's easy to calculate. If we have finite number of factors, that's also relatively easy to calculate. If we have number of qubits going to infinity, then we have an estimate for the width, or which we believe that is quite tight, but we don't have a proof. And so basically you can apply to many properties, but whether to be able to get a definite answer, you have to do some work in each of those cases. Yes?
For instance, you could ask about the threshold for being close to a product state. You fix a distance, epsilon. Ask for what the
Threshold
product
for
is
being
separated.
close
Close to.
to product states.
Yeah, in trace distance for some fixed distance.
In what sense?
The distance to product is less than some epsilon that you fix. And you ask for how the threshold.
So I think if you ask close in the Hilbert-Schmidt norm, then it's probably immediate. If you ask in the trace norm, then it's not that immediate, because when you see closeness to product state, it's no longer, product states of course are not convex, right? So there is a properties which aren't convex, to which the sets corresponding to them are not convex, will require some further care. It may be still possible, but it doesn't follow automatically from the scheme.
I guess a partial answer to that one is in the paper of Andreas and Debbie and Patrick, where they talk about the mutual information of generic states, which would also, I think, should give a control on the distance to product.
That will give you a bound, but it doesn't say if there's a
Yeah, I don't
threshold.
think this transition.
But the other, in one direction, but the other, it says if the environment is big enough, then you're very close to product. And in the other direction, you simply, I'm pretty sure you can show you're far away.
Yes, yeah, but this is very bad to mention because the size of the environment is basically a bit bigger than n.
Yeah.
Then you're already close enough to product.
Yeah,
Yeah, so but this is not really close enough for separable.
right.
I mean, not big enough for separable, because there's a very big difference between exactly separable and only close to separable.
Right.
Yeah, Martin.
So I think some interesting set of sets in between separable and the full set could be symmetric extendability. So that I ask, I choose a random state, how symmetrically extendable is it?
Yeah.
No. Yeah. So
I think some people are trying to calculate that.
okay.
So actually, I had a question and not only an answer, which is, what about, so you're talking about the trace distance, the trace distance, but what about if you look at the restricted classes of measurements like separable measurements? Do you, is that,
But
you get something nice from that?
you mean what? Okay, okay? So you want to approximate your random induced states by what? Using those measurements, no? Or what is? Or you want to detect what using those
I
measurements?
guess I want distance from separability in those. Maybe that's a more fine-grained, more difficult question.
Okay, so that is what I was saying before. So as soon as this S is a bit larger than n,
Yeah.
you're in the regime that your distance from separable is very small. Right? It takes up to what is d cubed, so n to the 3 over 2 until you actually enter the set of separable. So here. So there's a non-trivial regime in between.
But you could. I'm fairly sure that you could really describe basically how the dependence on the distance is on.
Another parameter.
Yeah.
So I have a question. This log, the occurrence of this log square, so it's entirely due to the MM star
Yes.
estimate.
Yes.
So if you had some kind of ad hoc way
Correct.
of
Exactly.
understanding this separable better, then you would also improve.
Yeah. That's the question in our paper. Yes.
So conversely, if this MM star estimate would be something non-trivial for the separable, would that mean that the threshold is also higher?
Well, this is actually not, that's not completely clear in full generality. Well, partly due to the fact that the set actually here is non-symmetric, so so you have to still go through several steps in the but basically it's a priori I think it's not exactly known whether this star estimate there is it's known that you may in some cases you may have a logarithm actually, and if it happens that the of course the expected value then happens to be well, and there are okay, so there are some cases when such things actually that logarithm actually appears, not only in the estimate but in the actual quantity, but it doesn't necessarily follow that immediately, at least from general theory.
So pretending I'm a token quantum chemist, we could also carry out this whole program for quantum chemistry, and ask for the probability to be in a set of convex combinations of Slater determinants, or I could also ask for these semi-definite relaxations, like I could ask for these P, T, and I don't know, whatever these conditions are called, GP and T1 and T2 conditions for existence. I mean, have you thought about this?
No. Not only, I even don't understand most of what you have said.
Just a change of plan.
I close the session. Let's continue doing the